How many positive integers below 2025 satisfy the inequality x squared over 20 minus floor of x squared over 20 is less than 0.2025? Note that the floor function, also known as the greatest integer function, outputs the highest integer lower than or equal to the input. For example, the floor of 1.5 is 1, while the floor of 20.99 is 20. I suggest that you give this problem a try first before picking at my solution. This question is from the final round of the 2025 edition of Math Count in the Philippines, which is a collegiate level math competition hosted by the Mathematics Teachers Association of the Philippines tertiary level. The key here is recognizing that the left side of the inequality is basically the fractional part of x squared over 20. If it isn't immediately obvious yet, let's consider simpler cases first. For example, let's say that the value of x squared over 20 is something like 1.5. The floor of 1.5 is 1, and the difference between 1.5 and 1 is 0.5, which is what we refer to as the fractional part of 1.5, which is basically the excess over an integer of that number. Meanwhile, if x squared over 20 is something like 20.25, then its floor is 20, and the difference between 20.25 and 20 is 0.25. And that's again the fractional part of the original number. In general, the definition of the greatest integer function and the fractional part function are tied by the equation floor x plus fractional part of x is equal to x, where the fractional part can take any non-negative value less than 1. Floor and fractional part functions are not generally discussed in detail in basic curriculum, at least in the Philippines, but I've seen their growing popularity in math contests recently. I suggest that you pay attention to the next steps here and hopefully gain insights on how to attack this type of problem on your own moving forward. Now, going back to the problem, we can rewrite the inequality as the fractional part of x squared over 20 being less than 0.2025. When we encounter fractional parts and greatest integer functions, the usual and very helpful trap is to identify first the cases when the expression becomes an integer. The expression x squared over 20 becomes an integer only when x squared is a multiple of 20. Hence, we let x squared be equal to 20k plus f, where k is an integer and f is a non-negative integer below 20. In other words, f is the remainder when x squared is divided by 20. Using this representation, we can rewrite x squared over 20 as k plus f over 20. Note that since k is an integer and f is below 20 by our definition, then the fractional part of this expression is simply f over 20. And so we get that f over 20 is less than 0.2025, which implies that f is less than 5. In other words, the solutions here are values of x squared that gives a remainder less than 5 when divided by 20. It's now a matter of identifying which values of x satisfy this requirement. I'm not sure if there's an easier way to do this other than just checking the values of x squared mod 20. When x is divisible by 20, so is x squared. So this case satisfies the requirement that the remainder of x squared is less than 5. When x is congruent to 1 mod 20, which is equivalent to saying that the remainder is 1 when divided by 20, the remainder of x squared when divided by 20 is 1, which satisfies the requirement. Numbers like 1, 21, 41, 61, and so on satisfy this modular congruence. When x is congruent to 2 mod 20, the remainder of x squared when divided by 20 is 4, which also satisfies the requirement. When x is congruent to 3, the remainder is 9, which does not satisfy the requirement. We do this for the rest and conclude that 10 out of the 20 possible remainders give a remainder less than 5. From 1 to 2020, there are 101 possible values for each case, which is basically the floor of 2020 divided by 20. From 2021 to 2025, there are only 2 valid values, namely 2021 and 2022. Therefore, there are a total of 1,012 positive integers below 2025 that satisfy the given inequality. And that's our final answer. So that's it for this video. I hope you learned something from me today. But if you have any questions, comments, suggestions, or violent reactions, just let me know in the comments. Thank you for watching and see you on the next one. Bye-bye.